Triangles, part 5. It was brought to my attention we didn't quite finish the previous activity. And on my pen, we didn't describe the regioselectivity. And we're going to go over here. And this is the answer for C. More electronegative O. On more subcarbon. That is the definition. When the word is more and more, what do you call it? Markalnikov. What does oxymercuration mean? Here's my answer. I love this answer. Oxymercuration. Done. You like my answer? It's a good answer. That's part D, color-coded. Stereoselectivity, anti or syn. Explain my choice. Oh, I didn't explain my choice in the first one. Because OH2 attacks which carbon? The more subcarbon. Can I just use sub or do I have to write substituted? I better write substitute. Carbon. Okay, and stereoselectivity is anti because of, thanks. He said backside attack. I think we got all the points there. And we got a fifth activity, the big finish today. Brings it all together. Here is what we did on the previous activity. We made this oxymercuration compound. It's got an oxygen and a mercury. And the part that we have to do here is provide the chemical which accomplishes the demercuration. So what does demercuration mean, just looking at these two pictures? It doesn't mean just that mercury is gone, which is true. That's half the answer. Sorry, provide the chemical. Oh, it's not asking what demercuration is, but mercury's gone. But what took its place? Just look at the product, please. Somebody said it already. What was it? Hydrogen. So wherever the mercury is, there's a new hydrogen, and it comes from, there's the old hydrogen that was already there. Just in case you're curious, here's the old hydrogen that was already there. Okay? The H comes from this chemical, where the H is actually a little like the H that had that lone pair, because it's attached to a less electronegative atom. Boron. And I need the right number of H's. One is wrong. I need the number of H's that makes this into an anion. So, yes, somebody said the right answer, but I'm going to go progressively towards it. If there's one H, it's +2. Because boron's in group 3, and you only have one bond. If it's 2 H's, boron's +1. If it's 3 H's, that's neutral, BH3. 4 is the right answer. You get a fourth bond. Now it's sharing 8 electrons is like owning 4 compared to periodic table where it owns 3. So all I'm doing this for is to teach you how to teach yourself to remember the formula based on chemistry. There's less memorizing if you understand chemistry. Seriously. So knowing your formal charges and how a boron is ever minus is very important, because you've got to remember, I need a minus, and then if you have a minus, you need a cation. It's NaBH4. And if you're curious, it looks like this. Na plus is a spectator. B with 4 H's is an anion. And it's called sodium borohydride. Why ide? Because the H's are attached to a less electronegative atom. You forgot that? B, 2.0, H, 2.1. Not allowed to forget it, everybody. Okay? And that's all you're responsible. Provide that chemical for me. Another way I test it is I give you these two things and ask you to provide this thing. Could you do it? Yeah, you should be able to do it. You got to learn this is the chemical that allows that transformation. And you have to learn that if you have this chemical and it reacts with this chemical, you should be able to predict this chemical as the product. The mercury's gone. It was replaced with an H. Sodium borohydride is the only thing that you're ever going to learn that does that. Well, the only thing you're going to learn in this course that does that. There's other things, but we're not concerned about them. Okay? And why is the product called a hydration product? Here's your answer. C5H8. One. No, it's not C5H. It's C6. C6. Not 12. Not 14, not 12, but 10. There. And this is C6H12. Oh, what's the difference between C6H10 and C6H12O? H2O. Okay. So I guess the answer B is summarized. I like using non-word answers every once in a while. You added water, right? Isn't that the definition of hydration? Add water to the formula. End of story. And then I'm going to remind you that you know several hydrations. Oh, part C is a great question. Part C in blue, you learned that if you reacted that chemical with water and sulfuric acid, you'd get the same result. Yes, question? No, stretching. Okay, very important. So why did we have to learn this new reaction that does the same thing and cost a lot more money? Like seriously, a lot more money. And we got mercury, which we have to get rid of. Why did we learn this mercury reaction? It seems terrible. We already had a reaction that did the same thing. It's in blue. And the answer is below. D and E. If you try H2O and H2SO4, you don't get this result this time at all. You get this result. You want me to prove it, even though it's not asked for? Here's an abbreviated mechanism, just based on intermediates. Based on intermediates only. You don't have to do this on a test. That's a nice cation, but it's not as nice as you can get. Don't talk to me about primary, secondary, tertiary. Don't do it. And how do we predict products of rearrangement? Students have trouble with that at first, and I understand why. It's a visual thing. So how do you predict what you get with this breaking and becoming a bond there? Copy everything except for the bond you broke. Do not move anything. Okay, so I'm copying everything as I see it, except for the bond I broke. And the bond you broke is next. It's now from here to here. Where's your cation? This guy had 4 bonds before. One of the bonds was to there. This guy had 4 bonds before, and it still has 4 bonds. This guy lost. You're saying, I'll never go from tertiary to secondary. That would be awful. Ring, strain, was drastically reduced. Right? That's more important than secondary versus tertiary. Forget about, just stop talking about hyperconjugation when you have ring size 4. It's irrelevant. There's a better word. Superfluous. Learn that word. Oh, lawyers love superfluous because they can speak the truth about something that really doesn't have any bearing on the case, but everything they're saying is true. But the big picture is like unimportant to them. Because they're speaking this little truth over here. The big picture wasn't talked about. The big picture is stability, right? Stability is the big picture. Hyperconjugate contributes to it. Hyperconjugation. Ring strain contributes to destabilization a lot more than hyperconjugation contributes to stabilization. Okay? So ring strain drastically reduced is why we got here. And how did you get this product? I'm not showing a full mechanism here. Next step, water attacks the cation, right? You get an oxonium, and then you neutralize the oxonium, and you have this exact picture here. There's a ring size 5 here, where the O will be 1 away from the bridge. Ring size 5 with a methyl on the bridge. There it is. This doesn't have ring size 4 or 3. It's only 5. Almost 0 ring strain in 5. And here's finally the answer to this question. Hydroboration slash hydroboration. Well, I'm doing a preview that's way ahead, like 5 minutes in our future. Oxymercuration slash demercuration. Suppresses rearrangements because there is no C+ intermediate. Okay. Suppresses rearrangement because there is no C+ intermediate. Remember, we did rearrangements with carbocation. That's the only rearrangements you've seen so far. This mechanism does not have a carbocation. So what are we going to do? We're going to say, oh, if you want just the straight up Markovnikov product without a rearrangement, that's when you needed to learn the mercury reaction. And here it is, the mercury reaction. Hg, OAC taken twice in step 1. H2O. So that left us with this result, which isn't the one I want. What's step 2? I got to get rid of the mercury that's not in the product. Boom. What chemical lets me do that? It's on this page. It needs to be written in this box. NaBH4. Yes, you have to know the second step of oxymercuration is demercuration and the chemical that accomplishes it. NaBH4. I will highlight it. We learned it here, so we could use it here. And there's no rearrangement. The skeleton stayed the same, didn't it? And the next one is our next reaction, but it's not a triangle day reaction. So, I mean, logically, I could stop today's lecture because it doesn't fit in triangle day. But I'm gonna tell you what the chemical is. In blue. It's another boron. BH3 equals borane. Kind of like methane, but a boron equivalent, right? That's where he got his name. Yeah. Hey. What's ALH3 called? It's not on this page. You'll never see ALH3, but you got to humor me. Alkenes. Sounds like a French name. That is a French name. It's not spelled right, but okay. BH3 followed by H2O2. What's that? Hydrogen peroxide, exactly. And you need hydroxide. Sorry, my box was too small. Or I was writing too big. And that mechanism we're going to do today. We're going to introduce it today. We want to spend a lot of time on that mechanism because it's our biggest mechanism of the semester. But I got a lot of tricks for you to help you learn it. So if I introduce it today and then we'll hit it hard on Monday again, then you'll have the weekend to practice. So it'll be activity 6 on the back of this page because it doesn't exist yet. So I'm going to stop this video. Wait. Oh, we already answered that, right? The answer is kind of up here. C, F, C, 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 C. Can I produce the same result? Yeah, we had a question. For that one? And smaller? And left. And stopping. After